Yeah, that's better. I brought some material samples, so I encourage you to have a look. So maybe you can pass them around. Here will be the first one. And once you manage to assemble them, you can send it to the next person. So yeah, we focus on. Can you hear? I think you can hear noise. We focus on curvy tree branches from the broadleaf forest. These kind of branches, they are usually wasted. They are just shipped and burned because it's hard to systematically use this kind of irregularly shaped material for higher value applications in construction or manufacturing. But there are some rare examples of craftsmanship where we can see that the natural shaped wood is actually used and has a function. And usually with the kind of more primitive tools of the past, it was difficult to work against the material, resulting in these kind of fascinating details. In contrast, today's wood production, it's characterized by standardization of raw material. So the raw material is standardized into orthogonal components and shipped and glued together with adhesives in order to achieve bigger dimensions, to not have to care about the grain orientation and knots in the wood and so on. But the broader research question that we're answering, what if we skip this step of standardization and work directly with the raw material? And we try to achieve this by leveraging 3D scanning to read the material and the unique shapes. And computational fabrication that can adapt the milling path to the unique shapes. There are previous attempts to leverage digital fabrication techniques with natural wood. And what we are trying to do is to make a system that works for 3D structures with automated design planning using only a 3-axis CNC machine. So a bit less focused on robots. But precedent work with natural wood, it has required a 6-axis 3D arm to make 3D structures, or it has been limited to 2D. So what we present is a novel fabrication method. It's the first system to leverage the diversity of curvatures of branches to make a 3D structure. Let me now present the process in more detail. First, we obtain branches. And because each shape is unique, we want to read these shapes. So we scan the branches. We also attach AR cube to the branch so that we can track the position. And then the system extracts the skeleton and radius. And we create a library of all the available material. And we want to make a general system, not just a one-off design. So we take a user-defined surface as the input for the system. And then we need to discretize this surface into branch-like components so that we can build this surface using the branches. So the system generates a reciprocal pattern of target curves that are then projected to the surface. And this kind of structure, the relatively thin branches, can make a relatively strong structure. So now we have a digital library of all the available material, and we have the design that we want to make. And the question is, which branch goes where? We have what we call an assignment challenge. So we developed an algorithm that can decide where and how to place each branch so that it best approximate the target design. And in the first step of that algorithm, we evaluate the difference between a target curve and a branch. We search for the tightest position between the two curves, and then we calculate the difference at this tightest position. So we obtain a full matrix of every pair of target curve skeletons with the differences or costs for each pair. But we can't just take the best branch for every target, because there's a possibility that the same branch is the best one for multiple targets, but actually we can only use it once. So we use an existing combinatorial optimization technique to minimize the sum of all the differences between the skeletons and targets of the structure. And then to account for possible deviations due to non-perfect fit, we also apply relaxation to further tighten the joints. And the next challenge is how to fabricate this design. We connect the branches with the cross-lap joints, and this image shows in green the milling paths of those joints. And the direction vectors of the milling cut is shown in pink. And since this is a three-dimensional structure, only looking at one branch, the milling directions of the joints are all different. And this is kind of the fabrication challenge. And the standard approach would be to use a robotic arm to approach the material from different directions. But robots capable of milling are quite expensive and mostly available in research labs, but not in the normal wood shops. And we are aiming to make a more accessible system. So we have made a different approach where the direction of the milling tool is constant, but instead the branch is repositioned by a human for each cut. And this is our fabrication system. So the camera can read the pose of the branch in relationship to the CNC machine. And then the user receives computer guidance in order to position the branch correctly. It's an audio-visual feedback system. And then the user fixes the branch in the vise, and the joint can be milled out. And this, let's see if the sound works. So this is what the
roll angle is set.
Maybe it's not that loud, but
The pitch angle is set. Fine-tuning the angle. Twist right. Twist left.
first the roll and
Twist
fix
left.
angles are set
Twist
separately.
left. Move down. Move down. Twist left.
And then the target angle is reached. And then this is what it looks like when the CNC machine mills out the joint at the speeded up rate. And yeah, shortly about implementation details. We use the multiple image capture for making the scan of the branches. The design planning and milling path generation is made with Python and Grasshopper inside Rhinoceros. And the post tracking with we use ARCO markers in OpenCV. And now to the results. So yeah, in order to produce results, we collected branches, 105 branches, and scanned them and attached AR cubes. We designed 7 NURB surfaces and applied the matching algorithm. The computation time to generate these are in between 30 seconds and 2 minutes. And you might wonder, what would it look like without this matching algorithm? So yeah, to have something to compare to, the first one is with the matching algorithm. The second one, we select a branch that does not match the surface. And in the third one, we use only straight rods representing engineered wood. And of course, yeah, only with diversely curved branches, and with the matching algorithm, does the branches actually follow the surface, resulting in tight intersections. And yeah, we also evaluated the system by fabricating a small dome structure. It has 17 branches and 24 joint connections, and it's assembled without adhesives, just dry assembly by hand. And here is virtual model of the dome and then overlapping with the scan of the finished structure to visually assess the difference between the fabricated result and the planned. So yeah, the fabrication took 32 hours, almost 1 week for this relatively small structure. One joint cut takes about 40 minutes, and most of the time is spent for actually milling the joint, because it's milled out in millimeter layers at an average of 30-40 layers for each joint, so it's quite time intensive. And then, yeah, finally, as part of our initial motivation was to make something structurally sound out of the relatively thin branches. So we also wanted to test the structure, so we performed the crush test, and it broke at 250 kilos. So in summary, we have developed this personal fabrication system that leveraged the diversity of wood. With this system, we can upcycle branches to become a construction material. And our two main contributions is one, the design planning system that is efficiently matching naturally curved branches with a target surface. And secondly, a fabrication system that augments a CNC machine with human mobility. So the matching algorithm, it has the potential to be reused for similar problem where you might want to match real material to an ideal design. And the fabrication process could also be used for other problems where you want to have a higher degree of freedom of direction of cutting, but you only have access to, for some reason, you just want to use a 3-axis CNC machine. And yeah, as for limitations, we only take single NURBS patches as input. We only consider the skeleton of the branch in the matching. We don't consider their other characteristics such as radius, knots, and texture, color that we don't consider in the matching. The fabrication process and material preparation is quite slow. And actually, the joint cut weakens the branch. That's the point of failure is at the joint. So as for future work, we could expand the system to take more types of input surfaces, such as an arbitrary mesh. And instead of using a surface, it's also possible to use a network of curve, for example, the skeleton of a piece of furniture. There's also room to increase the efficiency of the scanning and post-tracking technologies to achieve a little bit, make the material preparation less tedious. And finally, it would be interesting to explore completely different ways of joining the branches. And that's all from me today. Thank you for listening.